The universe was once a blinding fog where light could not travel. For nearly 400,000 years, space itself was invisible. This all changed in a single, monumental event called recombination, the moment the cosmos turned transparent for the very first time. By the end of this story, you will understand how that ancient flash of light connects directly to your own existence. We will uncover how a chaotic, formless blaze transformed into the structured cosmos we see today, and why the oldest light in the universe holds the blueprint for everything, including the atoms in your body. What does it feel like to trace your origins back to the very first dawn? For nearly 400,000 years, the entire cosmos was a searing, chaotic ocean of light and matter. This was not the dark, empty space we know today, but a thick, glowing fog so dense that light could not travel in a straight line for more than a minuscule distance. Picture a room filled with billions upon billions of tiny, frantic mirrors, each one a free-flying electron. Photons, the particles of light, would zap from one electron to the next, constantly scattered and redirected, trapped in an endless, dizzying pinball game. In this state, the universe was a brilliant, featureless blaze, a uniform soup of raw energy where atoms could not yet exist. The temperature was simply too high for protons to capture electrons and form stable unions. This era, often called the photon epoch, was defined by this intimate, turbulent marriage of matter and radiation. It was a cosmos of pure potential, a blank canvas of searing heat, waiting for a single, critical change in temperature to trigger the most profound transformation in history. From this formless inferno, the very first structures would one day emerge. This relentless expansion was the universe's great cooling mechanism. Think of it like a cosmic steam engine, releasing pressure and losing heat with every passing microsecond. The temperature fell at a staggering rate, from trillions of degrees down to a comparatively frigid few thousand. In this cooling crucible, the frantic chaos began to subside. The particles that had been zipping around at unimaginable speeds started to lose their kinetic energy, their furious dance slowing to a more manageable tempo. This shift in energy was everything. The electromagnetic forces that had once acted like powerful repelling magnets, keeping positively charged protons and negatively charged electrons fiercely apart, began to weaken. Their dominance was fading. For the first time in nearly 400,000 years, these opposing particles could get close enough to feel a different kind of pull, a gentler attraction that could potentially lead to a stable partnership. The universe was not just cooling down, it was calming down, creating a quiet but profound window of opportunity. This was the essential environmental shift, the necessary calm before the storm of creation. The stage was set not for another violent explosion, but for a binding event so fundamental it would alter the very fabric of reality, turning an impenetrable fog into a transparent universe. This gradual cosmic courtship unfolded as the universe cooled to a specific critical threshold. The temperature dropped to around 3000 Kelvin, a point where the chaotic energy of particles finally subsided enough for stable bonds to form. For the first time, the positively charged protons could reach out and capture the negatively charged electrons that had been their frenetic dance partners for millennia. This was not a violent collision, but a quiet, fundamental embrace. One by one, these pairs came together, creating the very first atoms in existence, the simplest and most abundant element, neutral hydrogen. This binding event, known as recombination, was a monumental shift in the balance of power. For nearly 400,000 years, the free electrons had acted as a pervasive fog, constantly bouncing light around and trapping it. But as they were captured into atoms, the number of these free, charged particles plummeted. The endless sea of tiny mirrors simply vanished. The scattering of photons, that dizzying pinball game, came to an abrupt and permanent end. This moment marks the official decoupling of matter and radiation. It was a cosmic divorce, a separation that allowed each to evolve independently for the rest of time. The formation of these simple atoms was the key that unlocked the cosmos. In a flash, on a universal timescale, the opaque prison for light was shattered. The universe, for the very first time, became a transparent medium. Space itself was suddenly and forever visible. But what happened to all that light, the very first to travel freely? Its journey was just beginning, and it carries a secret message from that first dawn. That newly liberated light did not just flood into an empty void. It streamed out from a specific universal boundary, a cosmic horizon we now call the last scattering surface. This is not a physical wall you could touch, but a fossilized moment in time, an immense spherical shell etched across the entire sky. It marks the final instant across the whole cosmos, when a typical photon bounced off a free electron for the very last time before being set free on its endless journey. Every point in our observable universe has its own last scattering surface, a personal horizon defining the oldest thing it can possibly see. This surface is a perfect snapshot of the universe at the moment of its birth into visibility, a photograph taken when the cosmos was just a newborn. The photons that escaped during that brief period have been traveling in near-perfect straight lines ever since, carrying with them an imprint of that ancient era. But their journey across an expanding cosmos has not been without consequence. The very fabric of space has stretched over the billions of years, and in doing so, it has stretched the light itself. Those once energetic photons, which began as visible light, have had their wavelengths pulled and lengthened. They have been transformed, cooled down into a faint microwave glow that now permeates all of space. This is the cosmic microwave background radiation we detect today. It is the oldest light in the universe, a direct messenger from its infancy, and it is not a perfectly uniform signal. By creating exquisitely detailed maps of this background glow, astronomers can read the subtle temperature variations, the tiny hotspots and cold spots that were imprinted on that last scattering surface. These minute fluctuations are the cosmic blueprints, the seeds of gravity that would one day pull matter together to form the very first galaxies, stars, and ultimately, planets like our own. But what created these all-important wrinkles in the fabric of the early universe, this newly liberated light flooding out from the cosmic horizon, is what we now call the cosmic microwave background. It is the universe's first light, the direct afterglow of its own fiery birth. This radiation is not concentrated in one place. It fills every single cubic centimeter of the observable cosmos. It is a uniform bath of energy, a whisper of microwave light that permeates the void, a direct remnant of that hot, dense past. But this light has undergone an incredible transformation. When it first broke free during recombination, it was not a faint microwave signal. It was a brilliant, searing glow of visible and ultraviolet light, a cosmic blaze that would have been blinding to any hypothetical observer. So what happened to all that brilliance? The answer lies in the relentless expansion of space itself. Over the course of billions of years, the very fabric of the cosmos has been stretching, and as it stretched, it pulled and elongated the wavelengths of this ancient light. This process, known as redshifting, gradually drained the light of its energy, cooling it down and shifting its color from visible blue to red, and finally into the invisible microwave part of the spectrum where we detect it today. The discovery of this cosmic background hum was one of the greatest accidents in scientific history. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent, mysterious static in a giant horn antenna. They pointed it at the sky, and no matter where they looked, this faint, uniform noise remained. They even famously cleaned out pigeon droppings from the antenna, thinking it was causing the problem, but the signal persisted. They had inadvertently stumbled upon the oldest signal in the universe, the cooled remnant of creation itself. This discovery provided the strongest evidence yet for the Big Bang theory, a monumental breakthrough that earned them the Nobel Prize. But the true value of the cosmic microwave background goes far beyond simply proving the universe had a beginning. This first light is a fossilized data stream. It is a cosmic blueprint that encodes, in its subtle patterns, the universe's initial conditions, its fundamental composition, and even clues to its ultimate fate. That faint, uniform microwave hum is not perfectly smooth. If you could see the universe's first light with the right kind of eyes, you would notice a breathtaking tapestry of subtle texture. Minuscule temperature variations, mere ripples of 1 part in 100,000, are painted across the entire cosmic canvas. These imperfections, known as anisotropies, are the universe's most important wrinkles. They are the fossilized imprints of quantum jitters from the very first instance of time, microscopic seeds that were stretched to cosmic proportions during the period of inflation. Each tiny hotspot on this map represents a region of the primordial universe that was ever so slightly denser and hotter than the average, while each cold spot was a little bit emptier and cooler. This might seem insignificant, but in the early cosmos, density was destiny. Those slightly overdense regions had just a little bit more gravitational pull. They acted as gentle wells, subtly attracting the neutral hydrogen gas that was now filling the transparent universe. Over hundreds of millions of years, gravity amplified these small differences. The gas slowly, inexorably, began to flow into these wells, pooling and condensing. The slight overdensities became greater overdensities, which then collapsed under their own weight to form the very first protogalactic clouds and eventually the brilliant fires of the first stars. Every galaxy, every cluster, and every vast cosmic web we see today grew from these infinitesimal seeds. By creating exquisitely detailed maps of these anisotropies with satellites like WMAP and Planck, cosmologists are essentially reading the universe's original genetic code. The pattern of hot and cold spots is a precise historical document, encoding fundamental truths about the cosmos. It tells us the exact age of the universe, its overall composition of dark matter and dark energy, and even the geometry of space itself. This ancient light is not just a relic, it is a direct blueprint for our existence, the original instruction set that guided the formation of everything we know. Yet, while this cosmic blueprint was being etched into the first light, a far more powerful force was already at work in the shadows. Dark matter, the invisible architect of the cosmos, was beginning its silent construction. This mysterious substance, which does not interact with light at all, was completely unaffected by the brilliant flash of recombination. While ordinary matter was finally cooling and combining into atoms, dark matter had already started to clump together under its own gravity, weaving a vast, unseen scaffolding across the universe. The subtle density variations we see in the cosmic microwave background, those tiny hotspots and cold spots, were not strong enough on their own to pull the universe into its grand structures. They were merely the seeds. It was the gravitational pull of these accumulating dark matter halos that provided the essential anchor, amplifying those small imperfections into deep gravitational wells. Think of it like this: if you were trying to build a city, you would first need a geographical foundation, like a series of hills and valleys, to guide where the roads and buildings go. In the early universe, dark matter created that foundational landscape. Its invisible mass carved out the cosmic terrain, the gentle slopes and profound valleys into which the neutral hydrogen gas, the ordinary matter, would eventually flow. This is why dark matter is often called the universe's skeleton. It provided the underlying structure, the hidden framework upon which everything visible would later be draped. We cannot see it, touch it, or interact with it directly with any form of light we know. Its presence is inferred entirely from its ghostly gravitational handshake. We see its signature in the way galaxies spin far too quickly to be held together by visible matter alone, and we detect its influence etched into the precise patterns of the cosmic microwave background itself. It dictated where the first galaxies would ignite and how they would be structured into the vast cosmic web we observe today. Yet, for all its foundational power, the fundamental nature of dark matter remains one of the most profound puzzles in all of physics. What is this ghostly substance that makes up most of the universe's matter? How did it guide the flow of the primordial gas that would one day become us? With a brilliant flash of the cosmic background radiation beginning its long fade into darkness, the universe entered its most silent chapter. This was the era known as the Dark Ages, a profound and lengthy interlude of pure blackness. The cosmos was now transparent and filled with neutral hydrogen gas, but it was also utterly dark. There were no stars, no galaxies, not a single point of light to pierce the overwhelming void. The only illumination was the fading afterglow of recombination itself, that first light stretching and cooling as it redshifted further into the invisible microwave spectrum with every passing moment. For hundreds of millions of years, this was the state of everything, a deep and featureless calm that stretched across the entirety of space. But this silence was deeply deceptive. It was not a period of cosmic stagnation or inactivity. It was a necessary pause, a gestational period where the most important work was happening in the dark. Beneath that placid surface, the invisible hand of gravity was tirelessly at work. The subtle density variations, the cosmic blueprints imprinted on the background radiation, were now acting as gentle guides. The dark matter scaffolding had already formed its hidden landscape of hills and valleys, and now the neutral hydrogen gas began to respond to its pull. Slowly, imperceptibly, atom by atom, this primordial gas began to drift. It flowed into the gravitational wells carved out by the dark matter, pooling and condensing in those regions of slightly higher density. What began as a faint whisper of accumulation grew steadily stronger over the eons. Vast, diffuse clouds of gas gathered, their internal pressure and heat building as they were compressed by their own growing weight. The Dark Ages were this crucial period of gravitational preparation, a silent, cosmic gathering of breath before the first brilliant fires could possibly ignite. This quiet era was the essential prelude to a revolution, the long, dark night that had to precede the very first dawn. That profound cosmic silence could not last forever. Deep within the densest clouds of primordial hydrogen gas, the long night was finally ending. The relentless compression by gravity had heated the gas cores to temperatures of over 10 million degrees, triggering the first nuclear fusion reactions. With a brilliant flash, the very first stars ignited, ending the Dark Ages and heralding the cosmic dawn. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our sun, and they burned with a ferocious, short-lived intensity. Their light was a stark, pure, ultraviolet blaze, and it unleashed a second great transformation upon the universe, an era known as the Epoch of Reionization. This was not a gentle transition. The intense radiation from these first stars and early galaxies was so powerful that it began to violently tear through the surrounding neutral hydrogen gas. Photon by photon, this ultraviolet light battered the atoms, ripping electrons away from their protons in a process we call ionization. The universe, which had so recently become a sea of neutral atoms, was now being systematically taken apart again. Vast bubbles of searing, ionized plasma began to form around these first sources of light, like clearings burned into a cosmic forest. This process did not make the entire universe opaque again, as it was during the early plasma soup. The gas was far too diffuse for that, but it did leave a distinct mark on the ancient light still traveling through space. As the photons from the cosmic microwave background passed through these newly formed bubbles of plasma, a small fraction of them scattered off the newly freed electrons, creating a subtle, polarized pattern that we can still detect today. Reionization was a messy and fragmented process, not a single, clean event. For hundreds of millions of years, these bubbles of ionized gas grew and merged, gradually eating away at the neutral hydrogen fog until the entire intergalactic medium was once again transparent to most wavelengths of light. This second great clearing of the cosmic atmosphere was fundamental. It cleared the path for the light from all future generations of galaxies to travel across the universe, unobstructed, allowing us to see the deep cosmos as it is today. Without this violent, brilliant dawn, the light from distant quasars and ancient galaxies would never have reached our telescopes. The universe had to be reborn in light a second time to become the transparent, observable expanse we now call home. These first stars were cosmic titans, born from a universe of pure potential. They are known to astronomers as population 3 stars, and they were fundamentally different from the stars we see in the night sky today. They formed from a pristine, elemental soup composed only of hydrogen and helium, the 2 simplest ingredients forged in the Big Bang. Without any heavier elements to help cool the collapsing gas clouds, gravity could work unchecked, pulling together immense amounts of material. The result was stars of almost unimaginable scale, monsters hundreds of times more massive than our own sun. They burned at ferocious temperatures, shining with a brilliant, bluish-white light and emitting torrents of ultraviolet radiation. But such a furious pace of nuclear fusion came at a steep cost. These stellar giants lived fast and died young, their brilliant lives measured in mere millions of years before they exhausted their fuel and met a cataclysmic end. Their intense ultraviolet light was the primary force that began to systematically re-ionize the universe. Think of these stars as cosmic lighthouses, and their UV radiation as a powerful, relentless beam. Where this beam swept through the vast clouds of neutral hydrogen gas, it acted like a cosmic blowtorch, striking individual atoms and violently stripping electrons away from their protons. This process systematically broke apart the very atoms that had formed during recombination, carving out vast, growing bubbles of ionized plasma in the neutral cosmic fog. This was the great reionization in action, a fundamental restructuring of the intergalactic medium driven by the light of these first stellar beacons. Yet their most profound legacy was written not in their lives but in their spectacular deaths. When these massive stars finally collapsed, they did so in titanic supernova explosions of unbelievable power. In these fleeting, violent moments, the alchemy of the universe advanced by leaps and bounds. The immense pressures and temperatures within these blasts forged entirely new kinds of atoms for the very first time. Elements like carbon, the backbone of life, oxygen, which we breathe, and iron, which courses through our blood, were synthesized in these stellar furnaces and then blasted out across space. This was the universe's first act of serious chemical enrichment. Before these supernova, the cosmos was a simple place, composed of only the two lightest elements. Afterward, it was seeded with the raw materials for everything to come. The dust and gas from these explosions eventually coalesced into a new generation of stars, but this time those stars were born with a richer inheritance. They contained traces of those heavy elements, allowing them to form differently and, crucially, to form rocky planets in orbit around them. Every atom of gold in a piece of jewelry, every molecule of calcium in your bones was forged in the heart of a long-dead star. These first stellar giants, though they shone for only a brief cosmic instant, were the essential architects of complexity. They lit up the darkness, cleared the cosmic atmosphere, and, in their final moments, provided the very building blocks from which planets, oceans, and life itself could one day arise. The violent brilliance of those first stars marked a revolution, but the preceding dark ages remain a cosmic mystery. To pierce that ancient veil, astronomers are tuning their instruments to a whisper from the hydrogen itself, a signal known as the 21-centimeter line. This faint radio emission is the fingerprint of neutral hydrogen, the very gas that filled the universe after recombination. It works like this. Inside a hydrogen atom, the single electron and the single proton each act like a tiny magnet, and they can spin in one of two ways, either aligned or opposed. When the electron's spin flips from the higher energy aligned state to the lower energy opposed state, the atom releases a tiny, specific amount of energy as a photon with a wavelength of exactly 21 centimeters. This is not a bright flash, but a quiet, fundamental hum emitted by every neutral hydrogen atom in the cosmos. The profound power of this signal lies in its ubiquity. During the Dark Ages and the subsequent epoch of reionization, the universe was flooded with this neutral gas, meaning it was also bathed in this specific 21-centimeter radio whisper. By focusing on this wavelength, we are not looking for a few bright objects. We are listening to the gas that constituted the universe itself. The expansion of space stretches this light, redshifting it to longer wavelengths the further back in time we look. This creates a cosmic tuning dial. By observing different wavelengths of this 21-centimeter signal, we can effectively slice through time, building a three-dimensional map of how the neutral hydrogen was distributed across the cosmos. We could watch as the first brilliant stars and galaxies ignited, and then track in real time across billions of years how their intense radiation carved out growing bubbles of ionized plasma, systematically devouring the neutral fog. This would reveal the precise timeline of reionization, showing us whether it was a swift, dramatic event or a slow, drawn-out process. Projects like the upcoming Square Kilometre Array, or SKA, are designed to be the ultimate receivers for this ancient signal. This colossal interferometer, with thousands of radio dishes spread across 2 continents, will have the sensitivity to detect this incredibly faint whisper from the dawn of time. Successfully mapping this signal would be like turning on a light in a darkened room and seeing the universe's very skeleton forming. It would show us the invisible scaffolding of dark matter, because that is where the neutral hydrogen would have pooled first. We would see the first structures, the faint overdensities that were the precursors to galaxies, and watch as they were illuminated and then systematically dismantled by the first starlight. This 21-centimeter signal acts as a cosmic ultrasound, allowing us to observe the universe's structure forming in the womb of the Dark Ages, providing a direct observational window into an era that has until now been pure theory. It is our best chance to witness our own cosmic origins, not as a fossilized afterglow, but as a dynamic, unfolding story. While the universe's first light paints a picture from 400,000 years after the Big Bang, a much older, more fundamental messenger was already traveling through the cosmos. Gravitational waves, the faint ripples in the very fabric of spacetime itself, could travel freely from the universe's very first instance, long before light was ever set free. Think of spacetime as a vast compound. A violent event like the colossal expansion of cosmic inflation or a sudden phase transition in the primordial universe would be like throwing a massive boulder into that pond. The impact sends powerful ripples radiating outward, warping the fabric of reality itself. These ripples are gravitational waves, and they propagate through everything, completely unaffected by the dense, blinding plasma that trapped light for so long. This means they carry a pristine, unaltered signal from a time that is completely inaccessible to traditional astronomy. The cosmic microwave background gives us a baby picture of the universe, but a background of primordial gravitational waves would be a recording of its first cry, a direct echo from the moment of its birth. The challenge is that these waves are incredibly faint. What we are trying to detect is not a single wave from a single event, but a cosmic hum, a stochastic background made from the combined whispers of countless violent processes all happening in that first fleeting fraction of a second. It would be like trying to hear the faint, collective roar of a distant ocean over the sound of every individual wave crashing on a nearby shore. To listen for this ancient signal, we need to go to space. Future observatories like the Laser Interferometer Space Antenna, or LISA, are being designed for this very purpose. This ambitious mission would consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart, connected by laser beams. A passing gravitational wave would ever so slightly stretch and squeeze the space between these spacecraft, changing the distance the lasers have to travel by a minuscule amount, less than the width of an atom. Detecting this primordial hum would be one of the most profound discoveries in all of science. It would provide direct evidence for physics at energy scales that are utterly impossible to recreate in any particle collider on Earth. This signal would open a brand new window onto the Planck epoch, the very first fleeting moments of time, allowing us to test our most fundamental theories about how space, time, and matter came into being. It would complement the picture from the CMB, giving us not just a snapshot of the infant universe, but a recording of its very first breaths. This single, brilliant flash of light from recombination was not the universe's first attempt at chemistry. Minutes after the Big Bang, a far earlier and more frenetic forge was already at work. During a brief window known as Big Bang nucleosynthesis, the entire cosmos was a scorching nuclear reactor, fusing the primordial soup of protons and neutrons into the first atomic nuclei. The predictions from this process are stunningly precise. The amounts of hydrogen and helium, and even the rare isotope deuterium, that we observe in the most ancient corners of space match the theoretical calculations almost perfectly. This remarkable agreement is one of the strongest pillars supporting our entire model of the Big Bang. Yet there is one stubborn, glaring anomaly, a single note that rings false in this otherwise harmonious symphony of creation. The universe seems to have a lithium problem. According to our best theories, the nuclear fires of the early cosmos should have produced a specific, calculable amount of the light element lithium-7. When we look at the oldest stars in our galaxy, which are composed of that pristine primordial material, we find only about 1/3 of the lithium that our models insist should be there. It is as if someone went through the universe's pantry and systematically removed 2 out of every 3 lithium atoms shortly after they were made. This is not a small miscalculation. This is a major discrepancy that has persisted for decades, resisting every conventional explanation. Where did all that primordial lithium go? The possibilities are as fascinating as they are profound. Perhaps our understanding of the nuclear physics itself is subtly incomplete. Maybe exotic, unknown particles from the dark sector were present in those first few minutes, interacting with normal matter and altering the delicate nuclear chain reactions that built the elements. Or the answer might lie not in the forge itself, but in the crucible that followed. Could the ancient stars that we use as our cosmic measuring sticks have somehow destroyed or hidden that lithium over billions of years, churning their outer layers and burying the evidence deep in their cores? Solving the lithium problem is far more than an academic exercise. It is a direct challenge to the standard model of cosmology, a tiny crack that could widen to reveal an entirely new layer of physics operating in the universe's infancy. Every proposed solution forces us to rethink fundamental assumptions. If new physics is the answer, it could point toward the nature of dark matter or reveal particles we have never dreamed of. If stellar processes are to blame, it would revolutionize our models of how the first stars lived and evolved. This missing lithium is a ghost from the first 3 minutes, a silent witness to a process we do not yet fully understand. Its absence is a clue, beckoning us to look deeper into that initial, furious blaze and discover what secret the universe is still keeping. This fundamental disagreement is known as the Hubble tension, and it represents a genuine crack in the foundation of modern cosmology. On one side, we have the pristine data from the cosmic microwave background. By meticulously analyzing the patterns in that ancient light, cosmologists can run the cosmic film backwards, calculating the universe's initial conditions and then projecting its expansion forward to the present day. This method gives us a very precise but indirect measurement of how fast the universe should be expanding now. The answer it gives is a specific, steady number. On the other side, we have direct observations of the contemporary universe. Astronomers use a sophisticated chain of measurements called the cosmic distance ladder, looking at pulsating stars known as Cepheid variables and cataclysmic supernova in relatively nearby galaxies. These objects act as standard candles, their known intrinsic brightness allowing us to calculate their distance and, in turn, the current expansion rate. The number this local method gives is consistently and undeniably higher. The early universe method suggests a slower, more sedate cosmic expansion, while the late universe observations point to a universe that is flying apart more quickly. The discrepancy is not large, only about 10%, but in the world of precision cosmology, where measurements are made with exquisite accuracy, that small gap is a yawning chasm. It is the difference between a theory that fits perfectly and one that is fundamentally missing a piece. So, what could be causing this rift in our cosmic reality? The possibilities are as thrilling as they are profound. The simplest explanation is that there is a hidden systematic error, a subtle miscalibration in one of our measurement techniques that we have not yet found. Perhaps our understanding of the Cepheid stars or the supernova is slightly off, throwing off the entire top rung of the distance ladder. But after years of intense scrutiny and improved measurements, the discrepancy has not vanished. It has hardened, leading many to suspect that we are not dealing with a mere measurement flaw, but with a whisper of new physics. This tension could be the first sign that our standard model of cosmology, the incredibly successful Lambda CDM model, is incomplete. What if dark energy, the mysterious force driving the accelerated expansion, is not constant as we have assumed? What if its strength has changed over time, or if a new, additional form of energy began to influence the cosmos long after recombination? Alternatively, perhaps Einstein's theory of general relativity, the bedrock of our cosmic understanding, requires a subtle modification on the largest scales. The resolution of the Hubble tension has become a primary driving force for the next generation of observatories, from the James Webb Space Telescope to the Vera Sea. Rubin Observatory, they are not just looking to confirm the discrepancy, but to pinpoint its origin. Is the conflict real, or is it an illusion created by our limited perspective? The answer will dictate the future of cosmology, potentially forcing us to rewrite the story of our universe's evolution and confront a reality far stranger than we ever imagined. The deaths of those first stellar giants did more than just seed the universe with new elements. When the most massive of these population 3 stars exhausted their fuel, their cores did not just explode outward. They collapsed inward, vanishing from the visible universe and leaving behind an infinitely deep gravitational pit. The very first black holes were born in these titanic implosions, the direct descendants of the first starlight. These primordial black holes were likely the initial seeds for the cosmic monsters we find today. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, weighing millions or even billions of times more than our Sun. How such behemoths grew so large so quickly is one of the great puzzles of cosmology. The collapse of those first massive stars provided the perfect starting point, a small, dense kernel of immense gravity that could begin its feast during the cosmic dawn. As these black holes formed, they did not sit quietly in the dark. They began to actively shape their newborn universe. In the era of reionization, these gravitational pits would have acted as cosmic engines. Gas from the surrounding neutral hydrogen, drawn in by their powerful pull, would have swirled around them in a frantic, heated accretion disk. This process releases a phenomenal amount of energy, not as starlight, but as a fierce radiation that would have blasted the surrounding gas, heating it and helping to drive the reionization process. A single growing black hole could effectively sterilize a large region of space around it, its intense radiation preventing gas from cooling and collapsing to form new stars. This creates a fascinating cosmic feedback loop. The black hole's growth can simultaneously quench star formation in its immediate vicinity, while its energy helps clear the galactic neighborhood, paving the way for future evolution. This intimate dance between a growing black hole and its host galaxy suggests a profound co-evolution, a relationship that shapes the destiny of both. The galaxy feeds the black hole, and the black hole, in turn, regulates the galaxy's growth. But the story of these first black holes might be even more fundamental. Some physicists have proposed a truly radical idea. What if a vast number of much smaller primordial black holes formed not from stars, but from the extreme density fluctuations in the very first moments after the Big Bang? These tiny, ancient black holes, some perhaps no more massive than an asteroid, could be scattered throughout the cosmos in incredible numbers, and if they are numerous enough, they could collectively account for the mysterious gravitational pull we attribute to dark matter. This idea, while still speculative, highlights how the search for the first black holes is not just about understanding gravity's traps. It is a search for the very architecture of the cosmos, a quest to see if the darkest objects in existence might hold the key to the universe's greatest missing piece. Those faint wrinkles in the cosmic background were the universe's original sketch, a set of instructions written in the language of density. Over billions of years, gravity took that simple blueprint and executed it on a monumental scale, weaving the sparse overdensities into the largest structure we know, the cosmic web. This is not a random scattering of galaxies. If you could step back and see the universe in its entirety, you would behold a vast, intricate architecture, a spider's web spun across the void on threads of dark matter. Galaxy clusters, each containing thousands of galaxies, shine like dense, brilliant knots. These knots are connected by long, faint filaments of gas and stars, forming the strands of the web. And between these strands lie the cosmic voids, immense, nearly empty regions of space that stretch for hundreds of millions of light years. This entire structure is a direct, logical outcome of gravity's relentless work. Think of a shallow hill on a newly formed landscape. Over time, rain will naturally flow downhill, carving streams and rivers that drain into ever larger basins. In the cosmos, the dark matter provided the foundational hills and valleys. The initial density variations were those gentle slopes. Gravity acted as the rain, pulling the neutral hydrogen gas, the cosmic water, to flow along the gravitational contours. The gas pooled in the deepest gravitational wells, which were the intersections of multiple dark matter filaments. It was at these busy cosmic intersections that galaxies preferentially formed, growing into the brilliant clusters we see today. The voids, in contrast, are the cosmic highlands, the regions that were largely drained of material, left as expansive deserts in an otherwise structured universe. Modern astronomical surveys, like the Sloan Digital Sky Survey, have painstakingly mapped the positions of millions of galaxies, and the resulting three-dimensional map reveals this web in stunning clarity. It is a cosmic fingerprint, a confirmation that the universe is fundamentally ordered. The pattern we see in the sky today is a scaled-up, evolved version of the pattern imprinted on the cosmic microwave background. This grand design, from the smallest quantum seed to the largest filament, tells a coherent story of a universe growing up according to a simple yet profoundly powerful set of gravitational rules. These ghostly particles have been whispering through the cosmos since its very first second. Neutrinos are among the most abundant particles in existence, yet they remain profoundly elusive, zipping through entire planets as if they were empty space. In that initial, unimaginably dense fireball of the Big Bang, the universe forged a staggering number of these phantoms, creating a cosmic neutrino background that predates even the cosmic microwave background. This sea of relic neutrinos is the second oldest thing in the universe, a vast, flowing current that has been shaping cosmic evolution from the shadows. Their influence stems from a unique property. In the hot, early universe, these particles moved at nearly the speed of light, making them what cosmologists call hot dark matter. This high velocity gave them a kind of cosmic restlessness, while the gravitational pull of cold dark matter was patiently pulling matter together into clumps. These speedy neutrinos were effectively smoothing things out. They would stream out of the tiniest, densest regions before gravity could get a proper grip, washing over the infant universe and suppressing the growth of the very smallest structures. It is a subtle but crucial effect, like a fine-grained sieve that only allows the larger clumps of matter to hold together. This neutrino drag left a distinct imprint on the cosmic web we see today, explaining why there are far fewer dwarf galaxies swarming around large galaxies than our models would otherwise predict. We cannot see this neutrino background directly with any telescope we currently possess, but we feel its gravitational fingerprint. The patterns of hot and cold in the cosmic microwave background are slightly different because of these particles. The subtle ways in which galaxy clusters are distributed across the voids and filaments of the cosmic web also bear the mark of their early influence. Pinpointing the exact effect of these relic neutrinos has become a primary goal for the next generation of observatories. Successfully measuring their impact would do more than just fill in a missing detail of cosmic history. It would provide a direct, uncontestable window into particle physics at energies so high we could never hope to recreate them on Earth. It would confirm a fundamental and long-standing prediction of the Big Bang, offering a glimpse into a universe that was just 1 second old, a realm dominated by ghosts that still flow through everything, including you, at this very moment. The quest to decode the universe's first light is accelerating with a new generation of cosmic listeners. The Simon's Observatory and the even more ambitious CMB-S4 project are not just upgrades, they are leaps into a new realm of precision. These next-generation telescopes, equipped with hundreds of thousands of ultra-sensitive detectors, will scan the sky from pristine, high-altitude sites in the Chilean desert. Their goal is to perceive the faintest whispers in the cosmic microwave background, signals so subtle they have remained hidden until now. One of their primary targets is a specific, elusive pattern in the light's polarization known as B modes. Think of the CMB light as having a specific orientation, a direction it vibrates. Most of the patterns we have mapped are E modes, which are curling patterns generated by the density fluctuations of ordinary matter. But primordial gravitational waves, the ripples from inflation itself, would have stretched and squeezed space-time in a way that imprints a distinct, swirling signature onto this ancient light, a signature we call B mode. Detecting this faint swirl would be like finding the direct fingerprint of inflation, a smoking gun for the universe's violent, exponential birth. Beyond this cosmic grail, these observatories will hunt for another ghostly signature, the mass of the neutrino. We know these particles exist in incredible numbers, but we have never been able to pin down exactly how much they weigh. Their collective gravity, however, has subtly influenced how the cosmic web formed, slightly suppressing the growth of the smallest galaxy clusters. By creating an exquisitely detailed map of the CMB and comparing it to the large-scale structure of the universe today, these experiments could measure this suppression with such precision that they would finally weigh the neutrino, settling a fundamental mystery in particle physics. The data flowing from these instruments will be a fire hose of information, providing the most stringent test yet of our entire standard model of cosmology. Every prediction about dark energy, dark matter, and the geometry of the universe will be scrutinized under this new, powerful lens. We are on the verge of either confirming our cosmic story with breathtaking certainty, or discovering the cracks that will lead us to an even deeper, more astonishing truth. This delicate chain of cosmic events, from that first flash of transparency to the formation of stars and planets, depended on a set of rules so precise it borders on the miraculous. The fundamental constants of nature, the very numbers that govern the strength of gravity, the power of the nuclear forces, and the initial density of the universe, all had to be exquisitely fine-tuned. Consider the force of gravity. If it were even slightly stronger, the universe would have collapsed back in on itself in a catastrophic big crunch long before stars could form. If it were slightly weaker, the cosmic expansion would have been so rapid that matter would have flown apart, never coalescing into the first galaxies. The nuclear forces are just as critical. The force that binds protons and neutrons in an atomic nucleus had to be strong enough to form stable elements like deuterium, a crucial stepping stone to helium, but not so strong that all the hydrogen would have been burned up in the early universe, leaving no fuel for the long-lived stars like our Sun. Even the initial density of the cosmos, the smoothness revealed in the cosmic microwave background, had to be just right. A slightly more chaotic, lumpier universe would have collapsed into a swarm of black holes, while a slightly smoother one would have remained a barren, featureless gas cloud forever. The event of recombination sits at the heart of this delicate balance. For neutral atoms to form, the electromagnetic force, the weak nuclear force, and the expansion rate all had to conspire to allow protons and electrons to combine at that exact moment in cosmic history. This staggering degree of fine-tuning leads to a profound and somewhat unsettling question. Why is the universe so perfectly calibrated for the emergence of complex life? This observation is formalized in what scientists call the Anthropic principle. In its simplest form, it suggests that the universe's fundamental parameters are compatible with the existence of observers because, well, we are here to observe it. We could not possibly find ourselves in a universe that did not allow for our existence. It sounds almost tautological, but it forces us to confront the sheer unlikelihood of our cosmic home. One compelling resolution to this puzzle is the concept of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of universes, each with its own random set of physical laws and constants, then it is no surprise that we find ourselves in one of the rare, lucky ones where the numbers lined up perfectly. In most universes, atoms may never have formed or stars may never have ignited. They would be stillborn cosmic landscapes, dark and lifeless. We, by our very nature as observers, can only exist in the tiny fraction of universes where the conditions are just right. This makes the moment of recombination far more than a historical curiosity. It was a critical, non-negotiable link in a chain of causality that stretches across 14 billion years, a chain that had to be forged from the very beginning with a specific, life-giving outcome in mind. The universe became transparent not by accident, but as a direct consequence of a deep, underlying order that made our future possible. That brilliant flash of the cosmic microwave background is more than our oldest photograph. It is the ultimate wall in time. We are forever peering out from our local point in the cosmos, but our view is fundamentally bounded by a cosmic horizon. This limit exists for a simple, profound reason. Light has a finite speed, and the universe has a finite age. We can only see the objects whose light has had enough time to travel across the void and reach us in these 14 billion years. The cosmic microwave background marks the final, impassable frontier for this kind of vision. It is the afterglow from the moment the universe became transparent, the oldest light that can possibly strike our telescopes. Gaze at any point in that microwave map, and you are looking back to a specific, universal moment, the era of recombination. But what about the time before that? What happened in the first 400,000 years when the cosmos was a searing, opaque plasma? That history is completely and permanently hidden from our direct view. Light from those earlier moments could not travel freely. It was constantly scattered and absorbed, trapping any information about that era behind an impenetrable fog. This creates an information barrier, a fundamental curtain drawn across the universe's earliest acts. Events of staggering importance, the inflationary burst that set everything in motion, the birth of the very first particles, even the potential creation of primordial black holes, all occurred on the far side of this veil. We are like investigators arriving at a crime scene long after the fact, able to study the aftermath in exquisite detail, but forever denied a recording of the event itself. This horizon is one of cosmology's greatest challenges, forcing scientists to become cosmic detectives. Without a direct view, they must search for clues left behind in the only evidence we have, the universe as it appears today. The subtle patterns in the cosmic microwave background, the large-scale structure of the galactic web, and the faint whisper of primordial gravitational waves are all indirect echoes from that hidden epoch. Each is a footprint left by a process we can no longer witness, a shadow on the cave wall that hints at the true shape of reality. Our entire understanding of the universe's birth is therefore a reconstruction, a brilliant and self-consistent story pieced together from these subtle secondary effects. Yet the horizon remains a silent reminder of the ultimate limits of our vision and a tantalizing border that defines the known from the forever unknown. This first visible moment forces us to confront a staggering philosophical puzzle. Our entire intuition about reality is built on a simple chain of cause and effect. Every event has a cause that came before it, but the Big Bang model, supported so powerfully by that ancient light, suggests something profoundly different. It proposes that time itself had a beginning. So what, then, does the question what happened before the Big Bang actually mean? If time began with the universe, then the concept of a before may be as meaningless as asking what is north of the North Pole. Our language and logic, forged in a world of continuous time, might simply break down at this ultimate horizon. This is the deep chasm where physics meets philosophy. Some frameworks, like the concept of a cyclic universe, attempt to resolve this by proposing an endless series of cosmic births and deaths. In this view, our Big Bang was not the absolute beginning, but merely the latest in an infinite cycle of expansion and contraction. A related and perhaps even more mind-bending idea is the multiverse. This suggests our entire cosmic history, from the Big Bang to the present, is just one isolated bubble in a vast, eternal, and ever-growing meta-universe. In such a reality, the moment of recombination was not the first time light traveled freely, but simply the first time it happened here within our particular cosmic domain. The significance of that first flash of transparency shifts dramatically. It is no longer the universal beginning, but our local origin story, the moment our own pocket of reality became independent and observable. This transforms the cosmic microwave background from a picture of the absolute beginning into a mere snapshot of our cosmic infancy, a baby picture from our own branch of a much larger and potentially infinite family tree. These ideas are not just speculative fantasies. They are serious attempts to grapple with the fundamental weirdness implied by our best theories. The moment we can observe that brilliant dawn of visibility acts as a mirror. It reflects back at us the limits of our own understanding, forcing us to ask not just how the universe began, but what it even means for something to begin at all. That faint cosmic whisper has demanded a revolution in our ability to listen. The relentless pursuit to map the universe's first light has not only expanded our minds, it has consistently broken new ground in engineering and technology. To detect a signal as subtle as the cosmic microwave background, scientists had to invent entirely new classes of instruments. They developed radio telescopes of astonishing sensitivity, capable of discerning a signal that is over 1 billion times fainter than the ambient radio noise of our own galaxy. They pushed the boundaries of cryogenics, learning to cool their detectors to within a fraction of absolute zero, just to quiet the thermal vibrations of the atoms within the machinery itself. And they created incredibly sophisticated algorithms to sift the cosmic signal from a storm of terrestrial interference, from satellite communications to the humble microwave oven. This technological legacy did not stay locked in an observatory. The low-noise amplifiers perfected for CMB experiments became a cornerstone of modern telecommunications, improving the clarity and reach of cell phone networks. The advanced signal processing techniques developed to clean cosmic data are now used in medical imaging, enhancing the resolution of MRI scans to peer into the human body with unprecedented detail. These are not coincidences, they are direct spin-offs. When you set out to observe the birth of the universe, you cannot use off-the-shelf technology. You have to invent what does not yet exist. This innovation extends to the very scale of human collaboration. A project like the Planck satellite was not the work of a single nation, but a symphony of international cooperation, involving scientists and engineers from across Europe and North America. The sheer volume of data it produced, a map of the entire sky with millions of pixels, each containing a deep story, forced the development of new big data analysis techniques that are now applied in fields from genomics to financial modeling. The search for our cosmic origins is a powerful engine for practical progress on Earth. It proves that by asking the most fundamental questions about where we came from, we inadvertently develop the tools to improve life here and now, building a better future by staring into the deepest past. Our existence is a direct echo of quantum whispers. Nearly 14 billion years ago, fluctuations tinier than a single proton were stretched across the cosmos during inflation, creating the microscopic seeds of all future structure. Those seeds were then frozen into the fabric of reality at the moment of recombination, imprinted as the faint temperature differences we now see in the cosmic microwave background. This was the universe's first and most important blueprint, a set of instructions written in the language of density and gravity. Over eons, gravity patiently executed this plan, amplifying those infinitesimal wrinkles into vast clouds of gas, then into the first brilliant stars, and eventually into the majestic galaxies we observe today. Within one such galaxy, on a rocky planet orbiting an unremarkable star, the specific elements forged in those stellar furnaces, carbon, oxygen, nitrogen, began to interact in ever more complex ways. They formed molecules, then self-replicating systems, and ultimately life itself. This life evolved over billions of years, developing nervous systems, brains, and finally, consciousness. We are that consciousness. Our ability to build telescopes to decode the cosmic microwave background and to trace our lineage back to the first atoms is the universe waking up and looking back at itself. The entire epic, from the formless quantum fog to the pondering human mind, is a single, unbroken chain of emergence. The universe did not just become transparent, it became self-aware, and we are its eyes and ears. The moment the universe turned transparent was not an end, but a magnificent beginning. It was the dawn of visibility itself, the opening of a cosmic stage upon which every galaxy, star, and planet would one day play its part. That faint, ubiquitous glow of the cosmic microwave background is our most profound connection to that pivotal event. It is a timeless echo, a message in a bottle from the dawn of time that continues to inform our deepest scientific inquiries and inspire our grandest philosophical wonder. This single, elegant transition from an opaque blaze to a clear expanse touches upon everything, from the ghostly grip of dark matter to the quantum seeds of all cosmic structure. It reminds us with humbling clarity that our very ability to see the stars and comprehend the cosmos is a direct consequence of that ancient clearing of the fog. Every photon that has ever traveled across the void to reach your eye began its journey thanks to that monumental shift. So the next time you find yourself beneath a dark, star-filled sky, let this knowledge settle in your mind. You are not just looking out into space, you are looking back in time, witnessing the final, glorious outcome of a story that started with a single, universal flash of light. If this journey through cosmic history sparked your curiosity, we have many more explorations into the universe's greatest mysteries waiting for you. Let us know in the comments what part of this profound event filled you with the most wonder.